Okay, let's go forward and talk about 3D transformations. So in 3D, scaling, we just add a dimension, right? So this looks exactly the same as our previous 2D matrix, except for now we're doing 3D points. So we're going to use 4D vectors, right? For the same reason, because our translation, we have to hide out here in this fourth column in order to make all of our math work. So we're going to go and use 4D vectors in order to do our 3D operations. So here's translation. So I think these are straightforward. Rotation gets a little bit more confusing. So if we consider rotations in 2D, it's commutative. We can rotate by 40, rotate by 20, or rotate by 20, rotate by 40. It doesn't matter. We get a 60-degree rotation. Not so with 3D rotations. So we could rotate around each of the axes, and this is how gimbals work. So certain robotic systems have things that work like this thing that you see on the bottom left. Is that animation? Is that GIF animation coming through? Do you guys see it? Yeah, okay. So, right, so we can rotate around our 3 axes. This is called Euler angles. And in fact, this is the way you will do it in your assignments because it's the easiest to, let me see, is this the way you'll do it in your assignments? No, you're also gonna have another operation available to you, I think, in the matrix library that you have. So these are the easiest to understand though. So let's take a look first. So if we wanna rotate around the x-axis, then nothing nothing changes if the x is 0, right? And then the y and the z values should change, right? So no, sorry, I don't mean if x equals 0. Whatever the x value is, it moves in that plane. The x value doesn't change, right? The y and the z values change if we go around the x-axis. So you see this matrix. This is exactly the same as the rotation matrix we had before. It's just moved into this corner. And because these are all zeros, the x-axis, nothing's gonna happen to it. We can write the same thing for the y-axis, except for we zero out it, or the z-axis and we zero out that. And so these are the Euler rotations around certain axes angles. So this is pretty convenient to write down what the matrix is, but it's not the most convenient to use. So I don't know how to make you guys do this operation. I'm going to switch back to the camera and I'm going to try to show it. The order that we do these things makes a difference. Okay, so here, okay, here's a phone. So this page is going to be my X and my Y, and Z is coming up out of this page. Okay, so we start with our phone in some position. And maybe I'll start with it flat. Now let's suppose we rotate around the Z-axis. This is rotation around the Z-axis. We could rotate around the Y-axis. I'm going to move it up a little bit so that I can do that. This is rotation around the Y-axis. This is rotation around the X-axis. Get rid of the picture of my kid acting stupid. Okay, now, so suppose we did a rotate around Z and then a rotate around X. So let's rotate around Z 90 and then rotate around X 90. So we got to here. Now let's do the opposite order. Now let's rotate around X 90 and then rotate around Z 90. We get to a different position. So the order that we choose to do these things is going to make some difference. So for rotations, it's not the same. So you just break out an object and make yourself some axes and try it out. You'll see that we don't get back to the same position. So what are we going to do now? And does it create some more problems? So it does in fact create some more problems. So the first problem it creates is called Gimble Lock. So these animated thing that's happening here, these things are called gimbals in robotics. And the difficulty comes when you align 2 of the planes. So you see in the second situation that we get to here, what's going on is that when the green and the magenta get aligned, then rotating the outer axis and rotating the blue axis both spin the airplane in the same way. And this is called Gimble Lock. So you get to a position where you basically lost a degree of freedom. This can happen when you're doing your rotations if you use Euler angles. Will it be a problem for you in your code? Some of you may encounter it. I don't think it'll be a huge problem to get out of, but you may encounter strange things when you start to stack up rotations. So that there's an alternate way to write these down, which may be useful and which your matrix library, I believe, has. So if we consider an arbitrary rotation axis in space, so here's my x, y, and z axes. I have this arbitrary red axis in space, and I want to rotate something around this axis. I can write down the angle I want to rotate and the direction, the XYZ direction of the axis. It always goes through the origin, but we have some axis that we want to do. And this produces some matrix, which is a lot uglier than that previous matrix, right? It's got all kinds of math to go solve what's going on in there. Okay, nevertheless, you have a utility function that can do that. So it's possible to also write down this more convenient way in order to get rotations around some arbitrary axis. Now, this is an alternate way to write rotations. So there's something else, which you may have heard of, called quaternions. So not in this class, but let me say something briefly about them. So quaternions are another way that you can deal with rotations. They have some nice properties. They don't have this Gimble Lock property. Interpolations in this space behave well. If you do interpolations on 3 Euler angles, you don't really get something that behaves nice. If you do interpolations and quaternions, you do. So what are quaternions? Okay, you remember imaginary numbers and complex numbers, right? You have these things where like I squared equals -1. So we're going to extend it. We're going to have I, j, and k, and I squared and j squared and k squared are all -1, and I times j times k is -1, and you end up with 4 numbers here because well, you have a vector with 4 numbers, which always needs to be unit normal, and blah blah blah. There's a bunch of go look at Wikipedia where I took this, and you can learn about it. So it would be a completely sensible thing to ask in a class like this, like the same way you wrote a vector library, go write yourself a quaternion library. But I'm not going to ask you to do that because I'd rather you learn about the matrix transforms. But in everything like Blender or Maya or any of these packages use, they're internally using quaternions for rotations. But at the time the graphics rendering happens, the part that we're focusing on in this class, these things get converted back to matrices. So nobody's passing a quaternion to their vertex shader. They're definitely passing a matrix to their vertex shader. So we're going to focus on that part in this class. So if somebody's feeling ambitious, go write yourself a quaternion library. The rules are actually not too complicated. It's not too hard to implement, but it's really hard to understand conceptually because you basically have this 4-dimensional imaginary number. And what does it really mean? It's hard to think about what does it really mean. So we're not doing that, but it's worth knowing the word and that they're used for rotations in graphics.